Hey, what's up, guys? This is Dr. Vivek Palipuram, and I'm bringing you the next lecturette in ENGR 250 Probability and Statistics for Engineering and Computer Science. We are still performing our phase 1 study where we are learning and applying probability theory, and now it's time for us to apply engineering ways of solving probability problems. In this lecturette, I'm going to discuss some families of discrete random variables. In my previous lecturette, I introduced you to what discrete random variables were all about, and we solved some problems using the probability mass functions of discrete random variables. But many times in science and engineering, we come across problems that belong to a particular family of random variables. In this class or in this lecturette, we are going to discuss some families of discrete random variables whose PMF takes a very specific form. Once we analyze that a problem belongs to one of these families of discrete random variables, all that we need to do is use the probability mass function from that particular family and apply it to our situation. There are different types of discrete random variables that one can work with. For example, there's Bernoulli random variables, geometric, binomial, and Pascal and Poisson random variable. There's one more random variable called the uniform random variable, which we'll also discuss in ENGR 250 Probability and Statistics for Engineering and Computer Science. In this particular lecturette video, I'm going to focus on these three families: Bernoulli random variable, geometric random variable, and binomial random variable. Remember, with these discrete random variable families, the problem becomes much more simple in the sense that you carefully read the problem statement and find out to which family does the given problem belong to. Once we identify the correct family of random variables to apply to that particular problem, we just use the probability mass function from that family and solve all kinds of probability problems. So let's get started with the families of discrete random variable, starting with Bernoulli random variable. Several times in engineering and science, you'll perform one single experiment which will have exactly two outcomes. Either it is going to produce you a 0 or it's going to give you a 1. Either it's going to be successful or it's going to be a failure. For example, electrical engineers at Intel may be interested in testing one IC at a time, or one where IC means integrated circuit. So an IC may either pass or fail. Similarly, computer engineers may be interested in testing different bits. Specifically, let's say that they're interested in testing one single bit. If that bit can be either 0 or 1. An engineering management employee at a company may be interested whether finding that the shipment has come or not. So that's again a Bernoulli random variable. Either the shipment has arrived, 1, where a random variable x takes the value equal to 1, or it may not have arrived, meaning the value of random variable x is equal to 0. So that's what Bernoulli random variables are all about. Bernoulli random variables help us to model those engineering experiments that have exactly two outcomes. Either it's a success, at which case the Bernoulli random variable x takes a value 1, or it can be a failure where Bernoulli random variable x takes in a value 0. Now the probability mass function for a Bernoulli random variable gives you the probability that the random variable capital X takes on a very specific value, small x. Now Bernoulli random variables can take only on two values. Either they can be 0 or they can be 1. So probability that x is equal to 0 is 1 minus p, and probability that x is equal to 1 is equal to p, which essentially tells you that a Bernoulli random variable or a Bernoulli experiment is going to succeed with probability p, and it is going to fail with probability 1 minus p. So that's Bernoulli random variables. However, in science and engineering, things are much more interesting than just performing one single experiment that has exactly two outcomes. Things get much more interesting when you perform a series of Bernoulli trials. Now remember guys, Bernoulli trials are a very specific example of independent trials where each trial is going to have the same probability model, aka a probability mass function of Bernoulli random variable. But things become much more interesting when we perform several of these Bernoulli trials. And depending on what we are interested in gives rise to different kinds of families of discrete random variables. For example, let's say that instead of checking just one single IC or integrated circuit, you are interested in checking multiple integrated circuits until you receive your first failure or first failing IC, integrated circuit. Now, you may test one single IC, the very first one, and it may fail, or there's a possibility that the first integrated circuit passes but the second one fails, and so forth. The number of times that you have to check or test the ICs until you get your first bad IC is going to be a random variable. Either you can get your first bad IC in the very first test, or you can get it in the second test or third test, fourth test, and so forth. If there's a facility that works absolutely perfectly, that may just keep testing the ICs but may never get a failed integrated circuit. So the number of times that you test the IC is going to be a random variable. So in this way, when we perform multiple Bernoulli trials and when we are interested in the very first failure, it gives rise to a new random variable family, which we are going to look into shortly. As an example, consider another case where you're, let's say, a computer engineer who's monitoring an n-bit sequence. Now, each bit position is a Bernoulli trial. It's going to have 1 with probability p, and it's going to have 0 with probability 1 minus p. Let's say that you test n bits and you're interested in k bit positions that take the value equal to 1. What's the probability of that? So this problem is solved using a specific class of discrete random variables, which I'm going to again discuss shortly. Essentially, the takeaway point here is by performing Bernoulli trials and looking into different aspects of that experiment gives rise to different families of discrete random variables. As an example, what I would like for you guys to do is pause your video here and use the methods that we have discussed so far in probability theory to solve this problem. So this problem goes something like this. Anytime a child throws a frisbee, the child's dog catches the frisbee with probability p, independent of whether the frisbee is caught in the previous throw or not. So each catch is independent of the other. So when the child throws the frisbee at one time, that's example of a Bernoulli trial. That's a single Bernoulli trial which has a success probability equal to p, upon which the dog catches the frisbee, and its failure probability is 1 minus p, meaning that the dog misses the catch. Now the child is performing several Bernoulli trials, and we are interested in one specific case, and that is when the dog catches the frisbee, it runs away with the frisbee, never to be seen again. So if the child continues to throw until the dog catches it, let x denote the number of times the frisbee is thrown. What you need to do is derive the probability mass function, PMF of x, where x is the number of times the frisbee is thrown. Now remember guys, probability mass function is generalized probability formula for a given problem. So what you can do is find the probability that x is equal to 1, find the probability that x is equal to 2, find the probability that x is equal to 3, meaning that the child throws frisbee 3 times, and on the third catch or on the third throw, the dog catches the frisbee and runs away. You will see a pattern emerging. Generalize that pattern in terms of x. That will give you the probability mass function. So please pause your video here and work on this problem. My another hint is apply tree diagrams. Once you're ready, you can unpause your video and I can show you the solution. Okay, I hope you guys got the chance to look into this problem. Now, carefully observe what x is. X is a random variable. X is a random variable which denotes the number of times the frisbee is thrown until the dog catches it. So naturally, x will take on values like 1, 2, 3, and so on, and this can go until infinity. So when you try to draw a tree diagram for this case, it is going to take a tree shape that can potentially go up till infinity, something like this. So at the root, when the very first time the frisbee is thrown, either it's going to be a catch or it's going to be a miss. It's going to be a catch with probability p, and it's going to be a miss with probability 1 minus p. If you consider this leaf, the value of the random variable x, which denotes the number of times the frisbee is thrown until the dog catches it, is equal to 1, because the dog has caught the frisbee in the very first throw. If, however, the first throw results in a miss, the second throw can result in a catch or a miss. Here, the value of x is equal to 2 because the frisbee has been thrown twice in order for the dog to catch it. And similarly, I can have a catch and a miss. At this leaf, the value of x is equal to 3. As I mentioned in my hint, we'll find the probabilities of these different leaves and then we'll try to generalize for any number of throw, or for any x number of throws. So probability of this particular leaf is p. Probability of this leaf is 1 minus p times p. Probability of this leaf right here is 1 minus p times 1 minus p times p, which is equal to 1 minus p squared times p. So notice what's happening. If x is equal to 1, the probability I can write it as 1 minus p to the 0 times p, because 1 minus p to the 0 is equal to 1. Probability that x is equal to 2 is 1 minus p times p. I can also write it as 1 minus p to the 2 minus 1. Probability that x is equal to 3 is 1 minus p squared times p. I can also write it as 1 minus p to the 3 minus 1 times p. So if you 3 minus 1 times p. So if you were try to generalize it for any throw small x, that probability will be 1 minus p to the x minus 1 times p. So the generalized probability formula for this case is probability that x is equal to small x is given by plugging the value of small x in the PMF, and that equation is 1 minus p to the x minus 1 times p. And this probability mass function is valid for these values of x. X has to be either 1, 2, 3, and so on, and until infinity. Now remember guys, x here starts at 1 because the child has to throw frisbee at least once in order for the dog to catch it. So x is going to start at 1 and it can go all the way to infinity. For all the other values of x which are invalid, probability mass function will always be equal to 0. Because if I were to ask you, hey, what's the probability that the dog catches the frisbee in x is equal to -1? -1 at the catch. -1 doesn't mean anything in this scenario. So that probability will be equal to 0. So this equation right here is what we call as the probability mass function for this particular problem. And using this PMF, I can solve all kinds of probability problems associated with this particular problem. For instance, I need to find out if p is equal to 0.2, what's the probability that the child will throw the frisbee more than 4 times? So I need to find what's the probability that x is greater than 4. And that can be found by performing 1 minus probability that x is less than or equal to 4, which is 1 minus probability that x is equal to 1, plus probability that x is equal to 2, plus probability that x is equal to 3, plus probability that x is equal to 4. Now to find these individual probabilities, I will directly use the PMF formula here and I will just plug and chug these values. So when I plug x is equal to 1, I get 1 minus p to the 0 times p. When I plug x is equal to 2, I get 1 minus p times p plus 1 minus p squared times p plus 1 minus p cubed times p. So that's the probability that the child has to throw a frisbee more than 4 times for the dog to catch it and run away and never to come back. So that's the gist of how to derive a probability mass function and how to use it to solve different probability problems. As it turns out, there are several engineering experiments that sound something similar to this frisbee problem here. For example, how many times do I test an IC until I get my very first failure? In this problem, in this frisbee problem, I am trying to model how many times does the child has to throw the frisbee for the dog to catch it and then just run away. Many science and engineering problems are kind of similar to this particular problem. And this problem pertains to a very specific class of random variables called the geometric random variable. And here's when you are going to use a geometric random variable. X in the previous problem, the number of times the child has to throw the frisbee, is actually a geometric random variable, which is defined as follows. If you perform Bernoulli trials repeatedly until the first success, then let's call the number of trials as n, then n is a geometric random variable. Specifically, The geometric random variable uses p as its parameter to form its probability mass function, where p is the probability of any one given Bernoulli trial to be successful. If x is the number of trials that you perform until the first success, then the probability mass function of a geometric random variable takes this specific form here, which we had derived in our previous problem. Depending on the value of p, you will have different probability mass functions, all of which will still belong to the geometric random variable class. So whenever you come across an engineering situation where you're repeatedly performing Bernoulli trials until the first success, then you're going to use the geometric random variable. For example, let's say that you are a production engineer and you're working in a production line where you're inspecting the quality of a particular product. You keep testing the product until you get the very first failed product. The number of times that you have to test until you get your first failed product, that can be modeled using the geometric random variable. So always remember, if you perform Bernoulli trials repeatedly until you get your first success or first observation that you're interested in, then the number of trials that you're going to perform is going to take the geometric random variables form. Okay, now what I would like for you guys to do is solve this problem and turn it for your Thursday's class by 10 a.m. So when a two-way paging system transmits a message, the probability that the message will be received by the pager it is sent to is p. When the pager receives the message, it transmits an acknowledgement signal, ACK, to the paging system. If the paging system does not receive ACK, it sends the message again. What is the probability mass function of n? The number of times the system sends the same message. So the system is sending the same message over and over again until it finally receives an acknowledgement. So n, the number of times this Bernoulli trial sending a message has to be performed, can be modeled using a geometric random variable. So in this case, apply the geometric random variable and answer these two questions for Thursday's class. Okay, now let's move on and try to solve this example problem. When a conventional paging system transmits a message, the probability that the message will be received by the pager is p. Just to be secure, or just to be sure that a message is received at least once, a system transmits the message n fixed number of times. So for example, if I have to be just sure that my destination is receiving my message, I'm just going to bombard it with n messages, and out of which it may drop some of the packets or drop some of the messages and receive certain number of messages. So let's assume that all transmissions are independent, and of course they are going to be Bernoulli trial because either the message is going to be received or not. What is the PMF of k? The number of times the pager receives the same message. You can pause your video here and try to solve this problem using independent trials concept. Once you're ready, I'm going to show you the answer to this problem. Okay, I hope you had the chance to solve this problem. So the system is sending n number of fixed messages. So there are n messages that are being sent, where each message will be either a success or it's going to be a failure. Now we are interested in k successes out of these n messages. If you were to consider one specific sequence, containing exactly k successes, then its probability is going to be p to the k, because success probability for any one message is p, and you are observing k successes times 1 minus p, which happens to be the failure probability, to the n minus k, where n minus k messages have failed. So that's going to be the probability of one specific sequence containing exactly k successes. However, there are multiple such sequences, each having the same probability, p to the k times 1 minus p to the n minus k. We need to add all of their probabilities to find the probability of k successes out of n. So this problem now boils down to finding out how many such sequences are there. Essentially, I'm asking you, in how many ways can you place k successes in those for those n messages? And the answer is n choose k, and each having the same probability, p to the k times 1 minus p to the n minus k. So probability of k successes out of n attempts is equal to n choose k times p to the k times 1 minus p to the n minus k. So this equation right here is the probability mass function of the previous problem. It is the generalized probability equation which you can use to find different kinds of probability. All you need to do is just plug in the right value of k which you are interested in. For example, in my previous case, let's say that I send the message n is equal to 10 times, and if the success probability of any given message is, let's say, 0.25, then the PMF takes this form: 10 choose k times 0.25 to the k times 0.75 to the n minus k. And using this PMF, I can answer different kinds of probability problems. For example, hey, out of 10 messages, what is the probability that 5 of them are successful? So I need to find the probability that k is equal to 5, which can be found by just plugging this value in this PMF form. So that gives me 10 choose 5 times 0.25 to the 5th times 0.75 to the 10 minus 5, which is also 5. So that's the probability for exactly 5 messages being successful out of 10. The PMF that we just derived belongs to a very specific family of a random variable called the binomial random variable. X is a binomial random variable which is characterized by 2 items: n, the number of fixed Bernoulli trials that you're performing, and p is the probability of each Bernoulli trial. Well, let me use k instead. So k is a binomial random variable, and the PMF of k has this form: probability that k is equal to small k is n choose k times p to the k times 1 minus p to the n minus k. Binomial random variables are used to model one specific engineering situation, which goes as follows. If you perform n fixed number of Bernoulli trials and you are interested in k successes, k is a random variable because k can be 0 success, k can be 1 success, k can be 2 successes, k can be 3 successes, and so on. K can be n successes. So k here, the number of successes out of the n fixed independent Bernoulli trials, is going to be a random variable. Specifically, it's going to be a binomial random variable which takes this particular PMF. As an example, let's say that you're an electrical engineer who is monitoring certain number of ICs. Let's say that your department or your group has handed you 15 integrated circuits, 15 ICs to test, where each IC is going to be either successful with probability p or failure with probability 1 minus p. Furthermore, if each of these tests are independent of each other, then k, the number of ICs that you find defective, is going to take a binomial random variables form. So whenever you perform fixed number of independent trials and you're interested in k number of successes, then k is a binomial random variable.